It is the 6th of February. That strikes somebody's birthday. I don't know whose. So every time that one object exerts a force on another object, the first object exerts a force back. And years ago, I remember having a student say, well, then how come when I throw a ball, I don't go hurtling backwards? Here, Michaela. How come I don't go hurtling backwards? I exerted enough force on the ball to get it over there. I accelerated the ball from 0 across the room. Why didn't I move back? So, force of me on ball is equal to the force of the ball on me.
Force is equal to mass times acceleration, and your mass is a lot greater.
Whole lot greater than that ball, yes. Because when you've got a really small object and a larger object, me, is exerting a force on it, the acceleration of the objects is proportional to their mass. If you have ever fired a shotgun and you've gotten kickback, the acceleration being put on that little tiny object, that little tiny projectile, the bullet, which fires it out of the muzzle at an incredibly high rate of speed, there's a force backward on you because there's an equal force exerted. That's kickback. If you have ever pushed something and fallen backwards yourself, same thing. So it's action-reaction pairs is how we think of this. And typically in the problems that we do, we're only dealing with one side of it. We don't typically calculate both sides. We do that a little bit if we get to impulse momentum and push-off stuff. This is where Holt Modern Physics' authors in all their infinite wisdom think you should learn about gravity and normal force, though you've actually been doing gravity and normal force for quite some time now, because they don't know how you could do most of the problems in this chapter without knowing this. So we talk about it early. Weight. I guess it would have helped to have had this conversation before the whole blue whale thing, huh? Weight is how attractive you are to the Earth. It's your mass times gravity. Your mass only changes based on how many Christmas cookies you eat or how many Christmas cookies you skip. Your weight changes based on what planet you're on. So you can go to a different gravitational field and with the same mass have a different weight because that is the force on you. We designate it as F sub g. We've been doing that. And it is always directly towards the center of whatever the gravity, the gravity field, where the gravity field's coming from. So towards the center of the Earth. Normal force, now, you know, I'm going to put an asterisk there. Mostly opposite of gravity. I'm going to put another asterisk here. Mostly or part of it. So it's generally, we should say, instead of opposite of gravity, it's generally in opposition to gravity. So not necessarily opposite, but always in opposition. And it's not always equal in magnitude to gravity, but it's often equal in magnitude to gravity, or at least part of gravity. Okay? It counters gravity. So it's always directly perpendicular to the contact surface. And we've started to see that on slopes. We're going to deal with a lot more slopes in this chapter. The overall opposition is to gravity because it's the reaction force to gravity. And this we designate as F sub n. I've been sloppy and I've been probably changing out lower and uppercase n's, but we should make it lowercase n and reserve uppercase n for F net. Now, while we're talking about opposing forces, we should talk about friction. And I would actually change that to motion. Friction opposes motion. So whatever direction the object is moving in, the friction is in the opposite direction. We'll eventually do at least one problem where we don't know what direction the object's moving in, so we don't know what direction the friction is in, and we have to figure that out. That's part of the problem. There are two kinds of friction. There's static and kinetic. And static friction is when nothing is moving. So I'm going to give you all a little practice. So at the point when the object is not moving, the static friction is equal to however much force you're applying. So for those of you who tried to drag the box, were you applying varying amounts of force and having it still not move? Yeah, I mean, you can ramp that force up slowly, 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 or if you're pushing the sled in football or whatever you're doing, you can keep applying force and it's still not moving. So you can have force applied equals 10 newtons, static friction. If it's not moving, static friction will equal 10 newtons. You can up that. Force applied, okay, I'm going to apply 15 newtons. If it's still not moving, the static force, the force of static friction, is now equal to that 15 newtons. You can keep increasing the amount of force that's applied, and until the moment when the object breaks loose and starts to move, whatever force you're applying is being opposed by an equal force. Because the object's at equilibrium. At equilibrium, sum of forces is 0. It ain't moving, not accelerating. So this is useful. They're equal and opposite. You can get rid of that. Kinetic friction is the thing that retards motion. That means to slow it down, but it's not great enough to prevent it. And once the applied force exceeds, what we talk about is force of static friction max, then that's when you have that break loose moment. That's when it starts to move. So then net external force is equal and opposite to the force of kinetic friction. Net external force. So not necessarily the force applied, but the net external force if there are no other forces in play. I'm sorry. Net external force is equal to the applied force minus the force of kinetic friction. Talk about this conceptually, and then we're going to introduce the coefficients, and then we're going to start calculating. So static friction is greater than kinetic friction. It takes more force to overcome that static friction than it does to keep an object moving that is moving. And it's all about the qualities of the surface. So the floors that we have in this building are really weird. They are slippery to some things. They are very, very high friction to other things because it's about the surface pair. Now, you can have a low friction surface like ice or greased metal that's going to be pretty low friction to all other materials, but you can have materials, here, let's try to push one of these chairs. The chairs with the rubber ends, have you noticed that they don't slide particularly well across this floor? Let's see how much of my weight I can, I'm playing a dangerous game here, folks. This may end badly. Okay, I don't feel like taking that all the way. I can't take another fall this week. So, it's been a bad week. That's relatively high friction. My shoes seem to slide more easily on this than the chair does. It's down to the surface pair. And so for any pair of surfaces, we have what we call the coefficient of friction. There's a coefficient of static friction, there's a coefficient of kinetic friction. And they're just a ratio of the maximum static friction to the normal force, in the case of the coefficient of static friction, and it's the ratio of kinetic friction to normal force in the case of the coefficient of kinetic friction. So that's mu sub s and mu sub k. Mu, mu, because the little u got its tail caught. That's how you remember it. And I have angry chemistry cat up there mewing hopelessly. If you want to add any cartoons to my science cartoons wall, you're welcome to. You can be immortalized on the science cartoons wall. Okay, so if we know the coefficient of friction, we can rearrange for other things. We can rearrange for normal force. We can rearrange for Well, we can do substitutions on the other axis. Oh, yeah. So we're going to start off with the 4C problems, which are a little bit more straightforward, and then we'll get into the substitution problem. Okay, so we put in Fs max, mg, 75 newtons over 24 kilograms times 9.81 meters per second squared. Should give us mu s, get a number. So I've got a raw answer, 0.31852, blah, blah, blah. And these are usually going to be fairly small decimals. What are the units here? Yeah! So, why? Why do you jump straight to that?
Because there aren't any on the picture up there.
Oh.
They cancel out.
They cancel out. It's a ratio. Ratios are unitless. So ratios are comparing two quantities, and here we're doing a ratio of the static frictional force to the normal force. If we do the dimensional analysis, a Newton is a kilogram meter per second squared, so we have newtons divided by kilogram meters per second squared. Units disappear. So final sig figged answer, we had 2 sig figs, so equals 0.32. And that's a fairly reasonable static frictional force. So all the problems on 4C are assigned, and then I'll get the worksheets ready for you. The 4C book problems are really pretty easy. So get going.